Hello there students, welcome to Edu-ca-te. In this video, we'll be covering vectors. We'll first define what a vector is, find the differences between vectors and scalars, cover properties of vectors, do vector addition, and lastly, do vector subtraction. Alright, what is a vector? A vector is a quantity that has both magnitude and direction. Let's write that down. A scalar is a quantity that only has magnitude and does not have a direction. If I draw this arrow over here, this is known as a vector. The size of the vector indicates the magnitude of the vector. And so if I draw a second arrow, this arrow is, as you can see, is much longer than this arrow, meaning that its magnitude is greater than this vector. So if I were to add some numerical values, we'd say that maybe this vector would be 2, and then this vector, since it's much larger or greater than this vector, then we'd say that this vector, we could say that this vector is 4, or could be any number, just as long as the length of the vector indicates the magnitude of the vector. If I draw a vector on a 2D or our Cartesian plane over here, this vector, we say it originates from the origin and terminates at some point x and y. A vector has a tail and a head. So this point over here where the vector originates from is known as the tail, and where the vector terminates or goes to is known as the head. Any vector that originates from the origin is known as a position vector. So the origin would be the point 0, 0. So all vectors that originate from this point, irregardless of the direction in which they point at, are known as position vectors. And we're now going to cover properties of vectors. Two vectors are said to be equal if both their magnitude and their direction is the same. So if we've got a Cartesian plane over here, and we've got a vector and another vector over here. Let's assume that these two vectors are equal of magnitude and the direction is the same. It is said that these two vectors are going to be equal. For vectors to be equal, their magnitude needs to be the same as well as their direction. Irregardless of where, on which quadrant or where they lie at, all that matters is that if their direction is the same and their magnitude is equal, then those vectors are said to be equal. So we could have another vector over here, a vector over here, a vector over there. As long as all of these vectors are equal in magnitude and they point in the same direction, they are said to be equal. To illustrate that something is a vector, we use a symbol with an arrow on top. The arrow indicates that this is a vector. So if we've got vector A, which we can denote it as a letter, or as a vector, which would be an arrow, we use an arrow on top to indicate that it is a vector, or we use a bold letter A to indicate that it is a vector. And if it is without an arrow on top, then it indicates that this could be the magnitude of a vector, or it could be a scalar. Going back to our Cartesian plane, this right here is known as the rectangular plane. And it could have any points that lie on this plane. Say for example 1, 2, 3, 1, 2, 3. Say for example we've got a point here at O which lies at 1, 1, where its x value is 1 and its y value is 1. This is known as the rectangular plane. When we introduce a r value and a theta value, then it becomes a plane polar coordinates, where r would be the hypotenuse of our triangle. So as you can see here, we've got r, which is the hypotenuse of our triangle. We've got x and y being the sides. Once we have r and theta, r being the hypotenuse and theta being the angle that lies between the hypotenuse and the horizontal axis, or the x-axis, then we've got our plane polar coordinates. And so to find, using SOHCAHTOA, we're able to find that sine theta would equal opposite, which is y, over hypotenuse, which would be r. So cos theta would be x over r, and then tan theta that would be y over x. Right. Since we know that this is a right angle triangle, we're able to use the theorem of Pythagoras, which states that the hypotenuse is the square root of x squared plus y squared. And if we want to find our x and y values, then let me just write that down. Multiplying both sides by r, this r would disappear, and then we'd have an r over here. Solving for y, we'd have r equal to sine theta. And if we want to solve for our x value, doing the exact same thing, where we multiply r on both sides of the equation, we get that x would equal to r cos theta. We can add vectors using two methods, one being the tail to head method and the other being the parallelogram method. The tail to head method is used when vectors follow each other or are consecutive to one another, in such that, say we've got vector A over here, and it is followed by vector B, such that the head of vector A touches the tail of vector B, then this method can be employed. And this is known as the tail to head method. And the vector that is a combination of vector A and vector B is known as our resultant vector. The resultant vector is the addition of two or more vectors, which in this case would be the addition of vector A and vector B. And our resultant would span from the tail of vector A to the head of vector B, because it's a combination of vector A and vector B. This, to repeat what I've just said, this is known as the tail to head method, that spans from the tail of the first vector to the head of the second vector. Another method that we can use is known as the parallelogram method. the parallelogram method. And this method is used when vectors are acting in directions that are away from each other. To show this graphically, if we have a vector, if we have the Cartesian plane over here, so this is the x-axis and this is the y-axis, and then we've got vector, our first vector, which goes in that direction, and our second vector going, that lies in the second quadrant. Then we use the parallelogram method to find the resultant vector. We've completed a parallelogram using these two vectors such that the magnitude or the length of this vector is equal to the length of that vector, and they both lie in the same direction, and the magnitude of this vector and the length of this vector is equal to the direction and the magnitude of that vector. To find our resultant, we would then draw a vector from the tail of both of these two vectors to the head of these two vectors, and this would be our complete parallelogram, and the vector that lies in between is known as our resultant vector. So if we name these vectors, naming this one as vector A, this one is vector B, our resultant vector, which is a combination of A and B, would be that vector. Combining two vectors gives you a third vector. So if we combine vector A and combine vector B, we'd get a third vector, which is a combination of vector A and B, and as shown, will be can be in a direction that is away from both vector B, or different direction from both vector B and vector A. To illustrate this, if we've got vector A and vector B, the resultant vector, which is a combination of vector A and vector B, it would be a combination of vector A and vector B and lies in a direction that is different from both vector A and vector B. So the resultant vector is also a vector, and it has its own direction as well as its own magnitude. It has been found that vectors obey the commutative law, which means that if we have vector A and vector B and vector A are going to equal. To illustrate this, if we have vector A being added to vector B, this is equal to vector B plus vector A. The order or the sequence in which you add vectors has no influence on the magnitude of the sum of the two vectors. So you could start with vector A or you could start with vector B. These are both equal. To illustrate these graphically, if we have vector A being added to vector B, using the tail to head method, the resultant vector, which is a combination of vector A and vector B, would lie in that direction. And if we start here in this example, we've started with vector A and then we've added it to vector B. So if we start with vector B, adding it to vector A, the resultant vector B plus A lies in the same direction as vector A plus B, and the magnitude of vector A plus B is equal to the magnitude of vector B plus A. And so it has been proven that vectors obey the commutative law, which states that it does not matter in which order you add vectors, it's still going to give you the same value or equal to the same value. It has also been found that vectors obey the associative law, which means that if we have vector A plus vector B being confined within brackets, adding it to vector C, this is equal to vector A plus the combination of, or the sum of vector B plus C. To illustrate this graphically, say we've got vector A being added to vector B, the resultant of these two vectors which would be vector A plus vector B. The resultant of these vectors, vector A and vector B, is a sum of these two vectors. And so vector A plus B is its own vector because, as you can see, its direction is different from vector A and vector B, as well as its magnitude is different from vector A and vector B. So when you add two vectors, you get a third vector which has a different magnitude and it could have a different direction. So vector A and B, we will treat it as its own separate vector. And so if I add vector C using the tilted method, we find that the resultant vector of vector A plus B in addition to vector C will give us another vector which is a combination of vector A plus B plus vector C. So as we can see, the resultant of vector A and B plus vector C, if we ignore vector A and B and treat vector A plus B as its own vector, we can see that vector A plus B plus vector C would give us a new resultant vector, which would be vector A plus B in brackets plus vector C. And so as we can see from what we've written here, A plus B, if we confine them within brackets and add it to C, it gives us, or it equals our resultant vector that we got over here. And so we'll prove what's on the right hand side. So if you've got vector A again, if you've got vector A being added to vector B, plus vector C. No, wait. So if we find the resultant of vector B plus vector C, we'll find that the resultant is the addition of vector B and vector C. And if we treat vector B plus vector C as its own separate vector, because it has its own direction and its magnitude, we can see that the addition of vector A plus vector B and C, vector B plus C, it will give us a resultant vector which will lie in that direction. And so, if we treat vector B and C as its own separate vector and adding it to vector A, we can see that the addition of these two vectors, this red vector and this blue vector, gives us a resultant vector or new vector, which is A plus B plus C, which is equal to what we have over here. We have proven that they are associative. We take our rectangular coordinate system over here. A unit vector is a vector that has a magnitude of 1 that we use to denote or to express the direction. So a unit vector has a magnitude of 1 and is a vector that is used to show direction. So in a 2D rectangular coordinate system, our unit vectors would be I cap, which has a magnitude of 1. This unit vector has a magnitude of 1 and lies in the x axis. And so it shows us that the direction is along the x-axis, and since it's a unit vector, or since we've said that it's a unit vector, then it means that its magnitude is 1. If we've got a unit vector along the y-axis, then we can express or denote it using the j cap, which shows that it's a unit vector along the y-axis and its magnitude is 1. And so, to summarize, a unit vector is a vector that has a magnitude of 1 and that is used to show direction. A vector can be expressed using its components. So if we take our coordinate system and we place a positional vector A, this vector has x and y components. So its x component would originate from the center until it reaches a value over there. And this, we can represent this as ax, and since we've said that it has a vector can be made out of two components, which is the x component and the y component in a 2D coordinate system, we can express this as ay, which would be the vector from the x-axis until or up until a point along the y-axis. And to write these down or to illustrate this mathematically, we will say that vector A, which would be the sum of ax I cap plus ay j cap. To repeat it again, we've said that these unit vectors are used to illustrate the direction. And so if we have this I cap, it means that vector ax lies along the x-axis, and j cap means that vector ay lies along the y-axis. And so if we've got vector A, which lies along that point, we'll name this vector A, and we've got another vector which we'll name as vector B, which maybe, let's say it lies along, that point, in that direction, which is the same as vector A. We've mentioned that vectors have components. In the two-dimensional coordinate system, vector A and vector B will have an x component, and they'd have a y component. But in the three-dimensional, they'd have three components. But since we're working with two dimensions, they would only have the x component and the y component. So to go to vector addition, or to add these two vectors, we'd say that, as we previously discussed, vector A has an x component and a y component. Same as vector B. As we've previously mentioned, that in the two-dimensional plane, a vector will have, or can have both an x component and a y component. But if it lies along either one of these axes, maybe along the x-axis, it will only have an x component, and if it lies along the y-axis, it will only have a y component. But since vector A lies in between, it will have both the x and the y component, since we're working in the two-dimension, or with a two-dimensional coordinate system. And so this means that vector A has an x component and a y component, and vector B will also have an x component as well as a y component. And so when adding vectors, you add the components that match with each other. And so you add the x component, which matches with the x component of A, which matches with the x component of B, and you add the y component of A, which matches with the y component of B. And so adding these two vectors, vector A plus vector B, so adding vector A and vector B, you find that the x component of vector A will add with the x component of vector B, and the y component of vector A will add with the y component of vector B. Adding these two vectors will give us a third vector, which is A and B, or the resultant of A and B. Subtracting two vectors also works in a similar way as addition. And so with match component of A, the component that lies in the x direction with the component that lies in the x direction, and the component of AY, the component of A which lies in the y direction with the component of B which lies in the y direction. And so if we say A vector A minus vector B. This means that the x component of vector A will subtract the x component of vector B along the x direction, and we'd have the y component of vector A subtracting the y component of vector B. Let's work with a quick example. Let's do an example of vector addition. If we've got vector A, which is equal to 20 So here we're given our two vectors, vector A and vector B. Adding these two vectors, as mentioned before, we'll have to add the components that lie in the x direction together and the components that lie in the y direction together. And so adding vector A with vector B, we'll find that And so what we've done here is that we've taken the components that match together and we've added them together. So we've taken the x component of vector A, adding it to the x component of vector B, and we've taken the y component of vector A, adding it to the y component of vector B. Adding these two vectors, we get positive multiplied by negative would give you a negative, meaning that 20 minus 5 gives you 15 in the I direction or in the x direction, and we have 10 plus 7 giving us 17 in the y direction. And so vector A and B, which is the resultant of vector A and B, is a new vector which lies in a direction and has a magnitude that is different from both vector A and vector B. And so if we work on a subtracting problem where we'll subtract vector A, vector B from vector A. And so matching the components again, we'd have negative multiplied by negative, which gives me a positive. 10 minus 7, which gives us a positive 3. We get that vector A minus vector B, which would give us these values. And this vector is a new vector separate from vector A and vector B. We've reached the end of the video. Thank you for watching. Make sure to like and subscribe.